Okay, another video, another learning goal. Let's do it. We're finally going to get into talking about the Fourier transform as well as dispersion spectroscopy. So I know we've heard that word Fourier transform before, so let's get into it. So there are two main classes of spectroscopy: Fourier transform spectroscopy and dispersion spectroscopy. And you have done both in your prior classes. So in FT, or Fourier transform spectroscopy, this is the, let's highlight some keywords here, simultaneous measurement of the absorption of light of many wavelengths at high spectral resolution. So basically what that means is all of the wavelengths are bombarded on the sample and the detector simultaneously. So typically this has to be any type of mode with small energy spacing between levels due to the large spectral resolution required, right? So the smaller the energy spacing is between levels, let's say with rotations or vibrations, or even in nuclear spin states with NMR, we have to have a really, really high resolution or a large spectral resolution to be able to do that. So the FT gives us that resolution. So dispersion spectroscopy is the measurement of the absorption of light of a single or narrow range of wavelengths, one at a time. So wavelengths are typically scanned using a diffraction grating, like we just talked about in the previous video. And generally, dispersion techniques are UV vis or even some X-ray spectroscopy due to the large spacing between energy levels and the not as strict requirement to have high spectral resolution. So this is a nice kind of like pictorial diagram of what the Fourier transform is. It is a complicated mathematical algorithm that converts a time-based signal into a frequency-based signal. And as a reminder, right, when we look at a spectrum, even though we typically are used to seeing wavelength on the x-axis, right, absorbance versus wavelength, we could also put that as absorbance versus frequency on the x-axis, right, to get our spectra, okay? So in the Fourier transform, because all of the wavelengths of our incident radiation are being detected simultaneously, we have to work through those in time. So for example, we might see the decay of an excited state look like the following. So that state decays in time. That's not going to really give us a useful spectrum. What we want is a peak at a specific frequency, right? So the Fourier transform does that for us. It will convert this decay signal in the time domain to a frequency domain. Now, this picture is related to NMR, so this is the free induction decay. But we can come up with similar pictures and ideas for IR spectroscopy. So let's take a look at that. This is called the Michelson interferometer, which is what makes an FTIR work. So I'm going to say FTIR. This is the principal mechanism in the instrument. And so the first thing I like to do when seeing these schematics of instruments is identify where my sample is and where my detector is. Okay, beautiful. So we can see light passing through a sample and hitting a detector. Great. So now we can see here our source lamp. And what will end up happening in the Michelson interferometer is we have the light passing through this chopper mirror, or sometimes it's referred to a beam splitter. And in a beam splitter, some of the light will transmit straight through, and some of it will reflect normal to that surface, or based on the angle of reflection. So the light that passes through the beam splitter will bombard onto this moving or vibrated mirror, as well as this fixed mirror. Those two signals will then recombine and pass through the detector. Now, when they are at a position that I like to refer to as the center burst, right here, typically where M and F are either equal to each other or some integer value to each other, we get maximum constructive interference. So constructive interference. And so, by the way, this diagram that we have here, this is called an interferogram. And that is actually the raw signal that an FTIR measures. Interferogram. So now you can see as the mirror moves, if you notice this, right, the x-axis is this distance that the mirror is moving. So as it moves off the center burst, we will get this convolution of destructive interference and constructive interference, and destructive interference and constructive interference. So we get a complicated interference pattern. Now, this mirror moves at a constant velocity. So even though on this interferogram, it's showing this as a function of distance, it really is a time-based measurement when we consider the fact that the mirror is moving at a constant velocity, and we can take that position of the mirror, d, and divide it by the velocity and get the time. Okay. So now to work out a spectrum from that, we consider finally here the Fourier transform algorithm. So here PD is our intensity as a function of distance that the mirror moves. And B as a function of nu is the intensity of our spectrum. So spectrum intensity, so like how big or small are the peaks. And PD really represents our interferogram, assuming I can spell. So now here is how this works out. Here's how this algorithm works. So suppose we just have like only 3 peaks coming from our sample, 1500, 3000, and 1000 wave number. And they all have different intensities. Well, because they're arriving at our detector simultaneously, we're going to see an interference pattern of those peaks. So that's what this plot is. So this is showing what those peaks would look like separately, but they will add constructively and destructively, so they will interfere with each other and give us this complicated pattern. So when we switch the position in those integrals, I mean, that's literally all the transform is now, right? You notice now that this function goes down here, and this function goes up here, and we change the fact that we're integrating now over a frequency versus integrating over a distance, which is really the same thing as integrating over time because our mirror is moving at a constant velocity. We can thus take the FT, the Fourier transform of this signal, and it will separate those peaks out for us, right? There they are, the 3000, the 1500, and the 1000. Pretty cool stuff, I think. And so as you might imagine, an actual FTIR spectrum is much more complicated than this. So there are thousands of interfering frequencies to give a super complicated interference pattern. So that's why looking at an interferogram on an IR spectra is not particularly useful. The Fourier transform, on the other hand, is. OK, so let's talk about backgrounding. So these are both important to do in FT techniques as well as dispersion techniques. And I drew all of these like random scattering events here because, as you might guess, that will, we might get some diffuse reflectance or specular reflectance off of the surface of our holder, right? So if we take first a background spectra, denoted by I naught, and of course a transmitted beam will come out of there. And then, of course, we then take a sample spectra where our I naught is still identical to our I. We will have a ratio of ratios, right? So technically, a spectrum is this ratio of ratios. So it'll look something like this. So if we look at the single beam of our background, it is going to have some distribution because we're using a broad lamp source. So let's say our intensity or our single beam background spectrum might look something like this, where there's no molecules in there and we've just got this big broad beam of light. Well, now when we go to look at our sample beam, our incident radiation was identical, but now there are some molecules in there that are absorbing some of that radiation. So our sample single beam will look something like this, where now certain wavelengths are taken out of that lamp due to the absorption of them. Okay? So then finally, when we take a ratio of these, whether it be absorbance, transmittance, optical depth, etc. So let's say we will now do, maybe the absorbance. A is negative log of, this would be the intensity of the sample over the intensity of the background, right? So we'll say that this is IB and this is IS. Then this feature right here, the big hump, will all wash out, and we will only see then the peaks, right? So we'll see now these nice, lovely peaks that cut out the background spectrum. Okay? Beautiful. And so this is why I always tell my students, if you stand on one foot when you record the background, stand on one foot when you record the sample. We really want to try and ratio out everything except the molecules that we've put into our sample. Okay, so we do a very similar thing, actually an identical thing for dispersion spectroscopy. However, typically in dispersion spectroscopy techniques, absorbance of the background single beam is usually not an issue. So we're typically only passing this like through our solvent, for example. So we're really just trying to wash out all of the diffuse reflectance and specular reflectance. So now, because I'm showing you here this dispersion technique, we have this monochromometer, which could be a prism or grating, to give us one wavelength at a time. So in a single beam spectrometer, we would typically have to put in a blank, just our solvent, record the background, and then put our sample in. The fancier dispersion spectrometers are called double beam spectrometers, and they have positions for both a reference cuvette as well as a sample cuvette, so that you don't have to take your sample in and out. So now, I mentioned in the dispersion technique, one wavelength is measured at a time. So with modern detectors now, we don't actually have to do that. So a very common modern detector is a CCD, a charged coupled device, is the same detector that's in your cell phone. And those CCD detectors have many, many pixels that are spatially oriented and can even be wavelength oriented. And so now, as you can imagine, if our incident beam comes in here, so suppose we have our sample and we now have our incident beam, and then I naught comes out, our transmitted beam, well, our grating is going to diffract all of those different wavelengths. And if we had just a very simple detector, we would have to pitch our grating in and out to bombard those different wavelengths onto the detector. However, because these CCDs have many, many pixels that can be arranged for different wavelengths, we can, in fact, measure all of the wavelengths simultaneously. This still is considered dispersion, however, because those wavelengths are still being mechanically separated by the grating. Okay, folks, so I know you've probably talked about this a lot in some of your other classes, but I wanted to make sure we could have an appreciation for why we have the Fourier transform technique and why we have the dispersion technique. Okay, I'll see you in the next video.